plug-and-play sanitization for TFHE, and Florian Bourse will give the talk and will be available to answer questions at the end of the presentation.
Hello everyone, thank you for the opportunity to present our work. I'm Florian Bourse and I'm going to talk about sanitization for fully homomorphic encryption. This is a joint work with Malika and Izabachène. First, let's start with some intuition and definition of what sanitization actually is, and we'll show how it can be used to build circuit-private fully homomorphic encryption. This is a typical application of an TFHE scheme. A user has some data X, and he wants to access a service which computes a function F. However, it doesn't want this data to be leaked, so he uses some encryption scheme to get a ciphertext containing his data. If the encryption scheme is fully homomorphic, this allows the server to apply the function F on the encrypted data and recover a ciphertext containing f of x. He can send back the encryption of f of x, and the user gets the information he wanted. The standard security requirement for encryption is semantic security. It basically says that the ciphertext does not reveal anything about the data, unless you have the secret key. Now, here we are interested in circuit privacy, which is the security property that preserves the privacy of the function f that has been applied. Meaning that when the user gets back the encryption of f of x, he can get f of x by decrypting, but he won't get any other information about f, even though he knows the secret key. You can have two ways to define this security with both these definitions. They have a computational counterpart when they rely on computational assumption, like the LWE harness assumption or ring LWE harness assumption. Or you can also have statistical security which holds without any assumption. And for both these definitions, you see, also you can have indistinguishability-based definition or simulation-based definition. Simulation-based definition are stronger, so this is what we prove in the paper, but to illustrate the work, I will use on the slides indistinguishability-based notions. Let's start with a quick example to see what is a violation of circuit privacy. With the LWE in dimension 1, with a modulo that is 2 to the 10, and let's just assume for a moment that the secret key is just 0. And here are two ciphertexts. If you want to know what the messages are in the ciphertext, we just take the second part and we subtract the first part times the secret key, so in this case 0, and then we round it either to 0, which gives us an encryption of 0, or if it's rounded to 512, it's an encryption of 1. Here in this case, you can see that both C0 and C1 have their second part that's lower than 256, so it means that they are encryption of 0. And let's just now define two functions. So I have a function f0 that takes two arguments and outputs the first one, and a function f1 that takes two arguments and outputs the second one. This function is also called a multiplexer when you take the third bit as input, or you can also see it as a conditional expression, just if then else. If I tell you that the evaluation of f beta on C0 and C1 gives you 42, 0, can you find the bit beta that's supposed to be hidden by circuit privacy? Well, since in this case the evaluation just gave C0, it's easy to see that beta is equal to 0. So this is a violation of circuit privacy, and this is what we want to avoid when we want to preserve the function. Let's now talk about sanitization. What is sanitization? If a fully homomorphic encryption scheme has sanitization, it means that it has another algorithm besides evaluation, encryption, and decryption, which is sanitize. It just takes a ciphertext and returns another ciphertext that contains the same message. However, the property that we want is that the new ciphertext doesn't depend on the original ciphertext, which means that if you take two ciphertexts that have the same message inside, which means that they decrypt to the same thing, if you apply sanitize to one of them, you cannot know which one was used. This is the definition of sanitization, and this is what we will try to build together. Let's now talk about circuit privacy, which is one of the main applications of sanitization. Circuit privacy says that if you have the two evaluations using the same ciphertext with two different functions that give the same result, you cannot know which one of them was used. So it's easy to get circuit privacy if you have a sanitized algorithm. You just apply it at the end of the evaluation. And now, since the output ciphertext is independent of the one that was before the sanitize, it doesn't depend on the function f that was used, but only on the value of f of x, on the result. Let's now show that you can do the other way around if you have bootstrapping. So what is bootstrapping? It's just basically homomorphically decrypting a ciphertext. So it's a function that takes a ciphertext and also takes ciphertext encryption of the secret key itself and does the eval algorithm on the secret key, on the bootstrapping key, which is the encryption of the secret key, on a circuit that depends on the ciphertext to get a new encryption of the same value. The difference here is that you start with any encryption and you have the guarantee that the new ciphertext has a small noise in it, which means that you can continue computing on it. So this is why it's in blue here, the small noise. If you have circuit privacy for the class of functions that is decryption for a fixed ciphertext, you can easily build a sanitized algorithm because you just have to do a bootstrapping basically and it works. Because if the evaluation doesn't depend on the function that was used, the input ciphertext is only used in the function, in the definition of the function. So if this is protected by circuit privacy, you have a sanitizing algorithm. Now let's talk about what randomization techniques exist and what we propose as new randomization techniques. The first one is very known and it's just called noise flooding. And I want to talk about a common misconception that circuit privacy is very easy. And this comes from the fact that these techniques works in almost any cases. However, I want to point out that the distributions have to be carefully studied. In Gentry's thesis, we see that the idea is very simple and it's just to add an encryption of zeros that has super polynomially larger noise to destroy all information in the noise part of the ciphertext. However, you have to be careful because if you take trivial ciphertext with just very large noise, even though the noise part of the ciphertext is flooded and you cannot recover information from it. In this case, since I know the first part of the encryption of 0 is 0, I can just look at it and I will know whether I had C0 or C1 at the beginning. So it's not enough to destroy information in the noise, which is something that will cause trouble for us later. This means that re-randomization just needs additional properties. You cannot just do noise flooding, but usually it will work. Another approach by Duca and Slay showed that even if the noise is not super polynomially larger, if you have access to bootstrapping, you can always do the following trick. If you have a rerun that introduces some randomness, so you won't get indistinguishability, but they will get closer to a canonical distribution, as long as they encrypt the same message. You can just do the bootstrapping and then this randomization step. And you repeat this multiple times, and every time you will get closer to the canonical distribution. So they show that even if you cannot do noise flooding because you have a polynomial size modulus, you can achieve sanitization this way, with the same techniques of re-randomization. Now, from both these examples, it's easy to see that choosing the way you re-randomize your input is very important when you want to build a sanitization algorithm. Usually what's done is that you have a public key that consists of n-log-q LW encryptions of 0, and you just take a random subset sum of those and add noise. with the leftover hash lemma, you can show statistical security. And if you have enough noise, you just do it once. If you don't have enough noise, you can do it multiple times using the techniques from Malika and Stele. In this work, we show that you can, instead of the order of nlog q LWE encryption of 0, you can only use one ring LWE encryption of 0. So now we're in the settings of rings, and we just do one encryption and add noise, and we show that it's enough. The difference here is that we don't rely on, we have to rely on the decisional ring LWE assumption. We don't have statistical security anymore. However, we believe that's not a big downside, because if the ring LWE assumption does not hold, the scheme wouldn't be used anyway, because this is the assumption the semantic security relies on. And in order to show that this works, we have to prove that the ciphertext is well distributed, even though the secret key is leaked. Because remember, the user knows the secret key, it shows it, and this is our adversary model. Now, in order to build sanitization, we will make use also of the technique of Bourse et al. For computing branching programs in GSW in a circuit private way. So the GSW is just encryptions, LWE encryptions of 0, you take a matrix of those, and to encrypt a bit beta, you either add or not the matrix G, which is a gadget matrix for which we know how to sample preimages with an algorithm G inverse. And to do circuit privacy for a multiplexer, which is the operation we've seen before, you just take the ciphertext C0 and you add C1 minus C0 multiplied by the encryption of beta. And this multiplication is done using the decomposition G inverse that cancels out with the G. They also need to add just a Gaussian noise, so we don't have any encryption of 0 in this case, which is very interesting. And they show that this just propagates the information in C beta and just add another distribution which is independent of this C0 and C1 of the input. This is what it looks like in a little picture. Now I show how we build circuit private blind rotate, which is a part of the bootstrapping algorithm that allows us to get sanitization. Let's start with the scheme of Bourse et al. For circuit private evaluation of branching programs. I won't talk in details about branching programs, but what you have to know is that it's basically a chain of multiplexers, and if you evaluate it correctly by adding rerun noise at each step, you can show, using fresh Gaussian sample each time, that at each step, all the states of the branching programs are well distributed with a canonical distribution. They need to add fresh Gaussian samples at each time because the Gaussian samples are present in the G inverse, so they cannot be reused over time, which is one of the things we fixed in our paper. And one of the main observations we did is that the TFHE blind rotate algorithm, which is a part of the bootstrapping that computes an encryption of x to the b minus SA from a ciphertext AB and the bootstrapping key, consists also of a chain of multiplexers. It starts from a fixed vector, test vector, and just does multiple multiplexer each time to multiply by x to the SI times AI. The main difference here is that instead of being with plain LWE ciphertext and GSWE ciphertext, we are working over rings. And in the case of TFHE, we work with a ring over modulo a power of 2, and the degree of the polynomials is also a power of 2, which is the most difficult case because of some properties I'll talk later about. So the first thing we do is just generalize the results to over rings. So we show that their noise analysis holds over ring. So we have the nice distribution lemma about discrete Gaussian. And the identity I showed you earlier that allows for this nice multiplexer circuit private evaluation also holds. However, it requires very large parameters that are impractical. So we cannot just use rerun as a Gaussian noise. We could if the parameters were very large, which is interesting in itself. But for the practical implementation, the parameters are too small for the result to hold. And this is because of the leftover hash lemma. Let's take a quick example. Leftover hash lemma asks that if you take two uniformly random vectors A and R, if you multiply them together, you should obtain something that's close to uniform. And this is usually the case because multiplying by a uniformly random vector is a universal hash function. However, this is only true if you have vectors in ZQ where Q is prime. In our ring, half the elements are invertible and half are not. So you can easily distinguish if you look at whether or not an element is invertible. If you take, for example, in dimension 1, two elements and multiply them together, there's only 1 in 4 chances that it will be invertible. However, in a uniformly distributed element, it would be a half. So it's very different. So you will require L to be big enough to overcome this issue. And in practice, our L is equal to 7. So we don't believe it's a good way to investigate. Instead, what we chose is to find a new version of rerun that was more efficient in the sense that we get rid of the downside of the huge public key, which is a big downside. So our version of the multiplexer evaluation, we have this rerun. It looks the same, but the rerun, instead of just a Gaussian noise, you have this encryption of 0 that's just based on ring GSW. And we can show that this has the same property. And we also go further and say that it's as if we had propagated the information in C beta, but instead of multiplying by C1 minus C0, we multiplied by 0. So now it doesn't depend anymore on the previous computations. So all the states are hidden. And let's now show how you can use it for rerun and what's our improved proof technique. So we said you cannot really do an induction forward because at each step, the G inverse would take the previous step of the accumulator, which already includes the previous noise. However, we showed that if you just add the noise at the end, you can do the induction backwards. That is, here, the rerun, if you use it to show statistical properties of this last step of plane rotate, you can replace it with the 0, and now you can move forward, and this rerun is not used anywhere else because we replaced by 0. So it's not present in the accumulator now. So this allows us to get a nice proof that we can just reuse the same rerun by putting it at the end. So we just have one encryption of 0 instead of having it 500 times. Now let's finally build our sanitize and put all bricks together. Let's recall the TFHE bootstrapping procedure, which consists in 4 algorithms. You start with your ciphertext that has a priori large noise. You do the modulus switching to get modulo twice the degree of the polynomial, and then you can do the blind rotate algorithm, which is a step that reduces the noise. And from this, you just extract only the coefficient of the polynomial you're interested in, and you can just key switch to get your new ciphertext. And we show that if you use our ciphertext, our circuit private version of the blind rotate algorithm, you can just show that from the ring LWE step, you only depend on x to the b minus sa, and from the extract step, you just depend on the output of the bootstrapping. So it is in fact a sanitized algorithm. We have to mention concurrent work by Kuzniak, which does roughly the same idea. So it uses Bourse et al. Results to show the nice properties on the noise. But since they are not using over rings, they have to use a rerun which has a large public key, and they do it after the extract to still be in a high dimension so that the noise can come from almost for free. Let's end with our empirical results and conclusion. We implemented our work and gave some parameters, and we showed that the sanitization is roughly 19 times longer than the bootstrap algorithm. However, we realized that most of this time was spent computing discrete Gaussians, small discrete Gaussians. So we also tried to pre-compute those to show what it would look like if you could do it in parallel or have specialized hardware to generate Gaussian for you. And we show that in this case, the overhead of the sanitization is very small compared to the bootstrapping operation, especially since you only need to do it once at the end of the eval function. And we also showed that the rerun functions that we propose is very fast and also has very small public key parameters, which is very efficient. And this is all of this has been done for 100 bits of security. And to recap, this is what we've done. So we've adapted most of the results from Bourse et al. Over rings, which also gives you multi-hop circuit privacy for branching programs over rings without circular security if your parameters are big enough, but they're not in practice. We also have a better proof by induction, better proof technique that reduces the parameters, and you can also use it to prove Bourse et al.'s result with adding the small noise only at the end. We also propose a new rerun implementation that greatly reduces the size of public keys. You can use it for ring LWE, but you can also use it for LWE samples by just extracting the LWE sample you want. And we use those building blocks to build sanitization with just one round of bootstrapping. We show it with Power 2 modules, but it's very easy to adapt it to prime modules, for example. You just have to work out the details. Thank you for listening, and I'm there for questions.